Okay, so in addition to the class last time, which of course the recording has been posted, I've also posted another example of graphing those rational functions where we do not only where the function's increasing, decreasing, concave up, concave down, points of inflection, maxes and mins, but also asymptotes. And so now you have one example from class. You have a second example from a separate video that I posted. Feel free to review that at your leisure. And the homework from Monday, of course, involves a lot of that same material. So I want to move on to the next section now, which is section 3.7. And I'm going to call it applied max-min. So the idea is we're going to take our skills that we've developed finding where a function is as large as possible or where it's as small as possible and apply it to actual problems that could conceivably be solved in the real world. So start with this. We wish to construct a box with no top beginning with a 6-foot by 4-foot sheet of cardboard. We cut squares from the corners. And fold up the sides of the box. Find the box of largest volume that can be so constructed. Oh, actually, let me make that question a little bit more specific. Find the dimensions Find the dimensions of the largest box, so the length, width, and height, the largest box that you can build in this way. Okay. So, first of all, before we even start, I hope everybody has an idea of what it is we're doing here. We're going to start with this rectangle of cardboard. We're going to cut out a corner here, a corner here, a corner here, and a corner here, and fold up the 4 sides. And that's going to form a box. The middle part of the cardboard is going to form the bottom of the box. And the 4 parts that we folded up are going to form the four sides of the box. So we're going to work through this in stages, the same way we work through a problem, or a similar way to when we work through a problem with related rates. So step one, same step one we had with related rates, we're going to draw a picture. So we start off with our 6-foot by 4-foot piece of cardboard. So 6 feet from there to there, and 4 feet from there to there. We're going to cut out squares from each corner. So we're just going to take our scissors and go cut, 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 cut there, and cut out this square. And cut out an identical square over here. And another one over here. And another one over here. And what we're left with is this plus sign. And basically what that gives us is a middle piece of the cardboard, which is a rectangle, and then 4 rectangular flaps. So the squares over here and over here and over here and over here are all gone. These are cut out. We removed them. We take these flaps and fold them up. This flap becomes one side of the box. This flap becomes another side of the box. This flap a third side, and this flap the fourth side, and this becomes the bottom of the box, and the box has no top at all. Does everybody understand the procedure so far? What we want to do? You can see that what we have a choice about is how big to make these flaps. If we cut just like a tiny square out from each corner, we're going to end up with a box with a really big bottom, but it's going to have a very tiny height. That box is not going to have a big volume. If, on the other hand, we cut out quite large squares, let's say we cut out that and this, we're going to have a box with a pretty big height, but it's going to have a really tiny bottom here. That box is also not going to have much volume. Somewhere in the middle, there's the right size square to cut out, such that of all the boxes you could build this way, that box has the biggest possible volume you could get. So before I go on, does everybody understand the problem? That we want to find the right size square to cut out from each corner so that the box we end up with has the biggest volume of any of these boxes we could possibly build. Can you give me a thumbs up? Or if there's something that's not clear, please stop me now. Okay, so some thumbs up coming. Awesome. Okay, so if you understand the problem, that's the first step. And if you have a good picture, you have a good chance of understanding the problem. Before we go on, I hope it's clear that the things we cut out have to be squares. If it's longer, say, in this way than it is in this way, then this side's not going to match up with that. And it hopefully will also be clear why these 4 squares have to be the same size, because if they're not, you're going to have sort of this wonky box where what we have over here is not a rectangle. It's going to be some sort of weird, I don't know what it's going to be, some sort of weird quadrilateral, but it's just not going to, this box is not going to be a sort of a rectangular box with right angles at the corners. So we end up with 4 squares, all the same size. That's what we cut out. And we form the box from what's left. Okay, so step 1, draw a picture. Step 2, define your variables. That can also look familiar. So generally, when we're defining variables, we're going to need a couple of variables. One for the thing we're trying to make as big as possible or as small as possible. And the other is going to be the thing that we have a control over. What we have control over in this problem is how big to make each of these squares. We could make a bigger square, a smaller square. That's what we have control over. I'm going to call this distance from here to here x. So x is the size of the square, the side length of each square that we cut out. Now, if that's x, this is x2, and this is x from here to here, and this is x because all these squares are the same size. So x is the side length of the square. And the thing that we're trying to maximize in this case is volume. So we don't have to make this fancy. V equals volume. Don't expect that your reader is going to be bowled over by the brilliance of your mnemonic that they're going to know V equals volume. Just say V equals volume. Let V equal volume. Anyway, something to let them know what the variable means. Okay, we're finished with step 1. We have a nice picture. We're finished with step 2. We have our variables. If you get through these 2 steps, the next step should be, if not easy, at least doable. Write a formula for the thing you're trying to make as big as possible or small as possible. Write a formula for the quantity you want to maximize or minimize. We're trying to maximize volume. And we like our formula to be a function of our variable, the thing that we have control over. We have control over x. So we know the volume of a box. I'm just going to write an intermediate line here. We know the volume of the box is equal to length times width times height. X there. Length times width times height. The volume of a box, length times width times height. Let's figure out what the length and the width and the height of this box is in terms of x. So the length of the box is the distance from here all the way over to here. In terms of x, we know this is x, and we know this is x. From there to there is x, and we know from there to there is x. What's the length of this as a little function involving x?
6 feet minus 2x.
Yeah, it's 6 minus 2x. We start off with 6 feet, and we lose x over here, and we fold this side up, and we lose x over here, and we fold that side up. So it's 6 minus 2x. So our length is exactly as you said, 6 minus 2x. And our width is going to be this distance from here to here. And it's the same thought process. You start with 4 feet. You lose an x over here, you lose an x over here when you fold these 2 sides up, and so we have 4 minus 2x here. And the height of the box is just that distance from there to there, but that's just x because all these squares have side length x. So 6 minus 2x, 4 minus 2x, x. And we can do a little bit of algebra here. Simplify that, or at least multiply it out. So let's see. We're going to FOIL 6 minus 2x times 4 minus 2x. I'm going to write the x squared stuff first. I'm just used to seeing it first. So 2x minus 2x times minus 2x is 4x squared. So 6 times minus 2x is minus 12x. Minus 2x times 4x is minus 8x. Minus 12x minus 8x is minus 20x. And 6 times 4 is 24. We still have that x hanging out over here. And we can multiply the x in 4x cubed minus 20x squared plus 24x. And so we've written volume as a function of x only, which is very nice. Step 4. Write an interval for your independent variable, the variable that you have control over. So for what values of x actually make any kind of sense? Now, we could argue a little bit about this. The smallest value of x that makes any kind of sense, we can see that I could cut out a square of size, 1/2 foot, like 6 inches by 6 inches, or 3 inches by 3 inches. I can't cut out a square of size minus 1 foot. That doesn't make any sense. I can't use any negative numbers. The question is, does it make sense to cut out a square of 0 by 0, in which case the whole box is just the bottom. This whole piece of cardboard is just the bottom of the box, and there are no sides at all. You could say, yes, that makes sense, or no, it doesn't make sense. Yes, if it makes sense, I have a box with volume 0. I'm going to actually include the endpoints. I'm going to use square brackets here, so we'll say that does make sense, just because it makes the math a little bit easier to do. I can understand if you say, well, that doesn't really make any sense. I can't put anything in a box if it doesn't have any sides. But at least saying I'm cutting out a box of side length 0 does make some sort of sense. So we'll start at 0. I will have square brackets. I can certainly understand your argument if you say, okay, well, round brackets would be more appropriate there. Now let me ask you, what's the biggest value of x that makes any kind of sense? This is a slightly harder question. We start off with
it has to be minus than 4.
Can you say that again?
It has to be minus, like it has to be less than 4.
It certainly has to be less than 4, but I think actually it has to be even smaller than that. If I cut out a box of side length 4, I go 4 over and 4 down, and then I go, from here I go 4 over and 4 up. These two squares actually overlap. It doesn't make sense for the squares to overlap. So with that in mind, what's the largest value that actually makes sense? Not 4, but if the squares can't overlap,
1.
Well, we can do bigger than 1. I could cut out 1.5. I could cut out 1.5 over here and 1.5 over here, and the squares wouldn't overlap. So I can get bigger than 1.
Can't you just put like 4, but like with that similar bracket, because we're not including 4, so that you could put like 3.9?
Well, the problem with 4 is if I go 4 over and 4 up, I've removed all this material over here, and then 4 over and 4 down. I can't even cut that square out because it overlaps with the first square I cut out. The biggest thing I can cut out, if somebody said it, is 2. If I cut a square of side length 2, I've gone 2 units over and 2 units down. And then if I cut out a square of side length 2 from the bottom, I go 2 units over and 2 units up. These two squares actually touch. I can't make them any bigger than that because then I've cut out material twice. I can't cut out the same piece of cardboard twice. So 2 is okay. In that case, I have a box with no bottom. It's just 2 flaps. But 2.1 is not okay because then the 2 squares overlap. So this comes from the geometry of the problem, that these squares can overlap. I can't cut out the same piece of cardboard more than once. So the biggest thing that makes any kind of sense is 2. I could certainly cut out 1.9 and 1.9, and these squares wouldn't quite touch. I can cut out 1.99 and 1.99, and these squares wouldn't touch. At 2, they touch, and any bigger than 2 doesn't make any kind of sense at all. So I heard somebody at some point say 1, and I can certainly understand why you'd say that, but don't forget that there are a lot of numbers between 1 and 2. There are infinitely many numbers between 1 and 2, 1.5, 1.6, 1.65. There's lots of numbers that are bigger than 1. So I think I understand what you meant or what you were thinking when you said 1. But I can actually cut out things up to size 2. So let's look at what we have now after step 4. We have a formula, and we have an interval. Now we're standing on familiar territory. You already know how to take a function and make it as big as possible or as small as possible on an interval. So now we've taken a sort of a real-world problem and reduced it back to something for which we already have techniques. So step 5, solve the max-min problem. In this case, it's a maximum problem. So you know exactly what to do. We have this function, we have this interval. Let's go ahead and solve this problem. The first step, as you know, is take the derivative of the original function, so v prime. Go ahead and take the derivative of that. It's just a polynomial, so that's not very hard. Three comes down, multiplies by 4, that's 12, x, 3 minus 1 is 2, minus 2 comes down, multiplies the minus 20, gives you minus 40, x to the 2 becomes a 1. So we won't even write that. X to the 1 is just x. And then 24x, the derivative of that is just 24. So what we're doing is finding the critical points. So we'll set v prime equal to 0. So we've done this problem before, all the way back at the beginning of the chapter. You take the derivative, you set it equal to 0, or look for places where it's not defined. So let's see, 12x squared minus 40x plus 24 equals 0. I think that might be a little easier to solve if I divide both sides by 4. So if I divide both sides by 4, that's 3x squared minus 10x plus 6. And I don't think that factors nicely. Let's go ahead and use the quadratic formula on it. So negative 10, 10 plus or minus the square root of negative 10 squared minus 4 times 3 times 6 all over 2 times 3. So let's see what we have here. We have negative 10, we have positive 10 plus or minus the square root, what's underneath the square root? 100 minus 12 times 6 is 72. So 100 minus 72, I guess, is 28 all over 6. So 10 plus or minus root 28 over 6. I'm running out of space on the blackboard, so I'm going to have to nix the problem. I want to leave the solution up so far, so hopefully everybody has that in their notes. So let's see. Root root 28 is root 7 times root 4. In other words, 2 root 7. So 10 plus or minus 2 root 7. Assuming I haven't made any mistakes. Hopefully, if somebody's checking my arithmetic. 12 times 6 is 72. And then 100 minus 72, 28. Yeah, okay. 2 root 7 over 6, and then I can factor 2 out from the top. So that's 2 times 5 plus or minus root 7 all over 6. And I can cancel that 2 with that. And so I end up with 5 plus or minus root 7 over 3. So that's really 2 numbers. That's 5 plus root 7 over 3 and 5 minus root 7 over 3. We're going to need our calculators now. So what we need are approximate decimal values for these guys. So I can pull up my calculator too, I guess. Okay, let's see. So 5, open parentheses, 5 plus root 7 divided by 3. I'm getting 2.54. This one's about 2.54. And 5 minus root 7 over 3. I'm getting about 0.78, 785-ish. Okay. Which one of these do I keep, and which one do I get rid of?
You get rid of 2.54.
Yeah, get rid of 2.54 because it's not in the interval. So remember, when we're solving a max-min problem, we're trying to maximize or minimize a function on a closed interval. We find all the critical points, which we just did. There are 2 of them. The next step is to get rid of whatever is not in the interval. 2.54 is not between 0 and 2. So get rid of that. Then you plug the remaining point in and both endpoints into the original function and see which is the biggest and which is the smallest. So let's go ahead. X and V, I'm going to plug in the endpoints, 0 and 2, and also 0.785 into the original function. If I plug 0 in, you can see that I get 0 minus 0 plus 0. We're plugging into the original function V. So I get 0. You plug 2 in, you'll see you also get 0. If you plug 0.785 in, maybe somebody will do this faster than I will. So let's see, 4 times 0.785 cubed minus 20 times 0.785 squared plus 24 times 0.785. I'm getting about 8.45-ish. And we look at these three numbers, 0, 0, and 8.45. That looks like the biggest one to me. And so this is the size, this is our x. That's how big we're going to cut out. That square is going to be about 0.785 feet by 0.785 feet. And that makes that gives us this volume. So step 6, write the answer to the question. Now, unfortunately, I had to erase the question, but it is still in your notes. What did I ask for?
The dimensions of the largest box that can be constructed in this way.
Yeah, exactly. I asked for the dimensions of the box. I asked for the length and the width and the height. I did not ask for the volume. That's the volume, 8.45 cubic meters. That's the volume, but that's not what I asked for. I asked for how the dimensions of the box, the length, width, and the height. So the length is going to be 6 minus 2 times 0.785. In other words, 6 minus 2 times 0.785, but 4.43 feet. Don't forget to include units in your answer. If there are units in the question, you don't have to carry the units all the way through because that's just be a mess. But in the answer, there should be units. The width is going to be 4 minus 2 times 0.785. The length was 6 minus 2.785. The width is going to be 4 minus 2.785, which is going to be about 2.43 feet. And the height is just 0.785 feet. And that's our answer. Don't have to put a box around it, but there's a lot on the blackboard, so there it is. How do you feel about this method? Is everybody okay?
Yes.
Cool. Are there any questions at this point?
I have a question.
Yes, absolutely.
For like when you were doing the quadratic formula, like on the left side, when
Oh,
you got rid of the 10, like how did you do that?
So how do they go from here to here?
Yeah, basically.
I just factored so these two terms both have a 2 in them. So I just factored a 2 out, and then that left a 5 in this first term. So 2 times 5 is 10, and 2 times root 7 is 2 root 7.
Okay.
But I should point out that if you don't like all this sort of mucking about with square roots, you could have just gone back over here when you had 10 plus or minus root 28 over 6, and you could have used your calculator at that point. So if this is your idea of a good time, just use your calculator at this point. I'm just used to simplifying things. I don't know what to say. My high school teachers had an indelible effect on me, and now I just can't help it. But if that's not helpful for you, just go ahead and use your calculator at this point, and you would get these same two numbers. You would still get 2.54 and 0.785, and just get rid of this one again because it's not in the interval 0 to 2. Are there any other questions? Okay, let's do another one. Does everybody have everything copied down? I guess as I said before, the beauty of this online thing is you will have a complete record of the class, so you can look it up later and then pause to your heart's content. So I'm going to get rid of this. squeeze one more in. Maybe. Now here's another example. And this example has a twist that didn't appear in the first problem. So a rancher wishes to fence off a rectangular pasture adjacent to a river. The riverbank will form one side of the rectangle. It doesn't need to be fenced. The rancher is going to fence the other three sides. So I'm going to fence off a rectangular pasture adjacent to a river, and the riverbank forms one side of the rectangle. That way the cattle can just drink right from the water, and presumably they can't swim away. And that side of the rectangle doesn't need to be fenced. So she has 1,000 meters of fencing for the other three sides. And I'm going to ask for the dimensions again. The dimensions of the largest pasture she can enclose. So a rancher wishes to fence off a rectangular pasture adjacent to a river. The riverbank's going to form one side of the rectangle, and it doesn't need to be fenced. There's 1,000 meters of fencing for the other three sides. Find the dimension, the length and the width, no height this time, of the largest rectangular pasture that can be enclosed. So let's go through our steps. Step one, draw a picture. So like here's our river. That's all water here. And we're going to fence in our rectangular pasture. So we're looking down from like the sky. This is like a map. And we're going to fence that side and fence this side and fence this side. But the cattle can come right up to the water's edge and drink, but they're not going to swim away. So we don't need to fence that side. Step one, draw a picture. Step two, define variables. So I can call this maybe, let's say, x and this x and this y. And I also need the variable for area. That's what I'm trying to maximize, the area. So step one and step two are finished. Now Now, step 3, so step 1, you don't have to write step 1 and step 2 and whatever when you're doing your problem. Step 2, variables. Step 3, I'm going to write step 3 for a second. Write a formula for the thing you're trying to make as big as possible or as small as possible. So area is what we're trying to maximize. And that's just length times width. So that's just going to be, y times x, or x times y if you like. Now, we run into a bit of a snag that here we have more than one variable on the right-hand side. And so if that happens, I'm going to call this step 3b. If you have more than one independent variable, get rid of one. We don't really have more than one independent variable because the bigger x is, the less fencing we have for y. So if we have more than one independent variable, which we didn't last time, but we do this time, use information in the problem to get rid of one. So in Calculus 1 and in Calculus 2, we are pretty much limited to one independent variable. We don't know what to do with more than one independent variable, although for those of you that eventually end up in Calculus 3, you will be working in exactly that context with more than one independent variable. Okay, back in the problem. What piece of information have we not used yet that connects x and y? We were given a piece of information in the problem that connects x and y. We haven't used it yet.
Is it the 1,000 meters of fencing?
Yes, 1,000 meters of fencing. That's as much fencing as we have. So this plus this is 1,000. In other words, x plus y plus x, or 2x plus y equals 1,000. Exactly as you said, 2x plus y equals 1,000. That's how much fencing we have. We haven't used that information yet. Now we have. And I can use this to solve for one of my variables. I'm just going to solve for y. So y equals 1,000 minus 2x. Just getting y by itself. Down here. Now I can take that, and in my original formula, wherever I see a y, I can replace it with 1,000 minus 2x. So a equals, instead of writing y, I'm going to write 1,000 minus 2x times x. And I can multiply this all together. 1,000x minus 2x squared. And now I have a formula with just one independent variable. That's great. So we didn't have to do this step in the first problem because we only had one independent variable. Here we were stuck with two. We had to get rid of one. Let's go ahead and write down our interval. The smallest and the biggest x that can possibly make any sense. We could have x equals, like 1 foot, and then we go over like 998 feet, and then back up 1 foot. I don't know. I don't think cattle would be very interested in a pasture that was only 1 foot wide, but we could definitely do that. We could go 6 inches and then go over 999 feet. That's not going to be a very big pasture, and I don't think the cattle are going to be very interested in that. The smallest value of X that makes any kind of sense is 0. Certainly, we can't use -1 or anything like that. If we do that, we just run 1,000 meters of fence right along the edge of the water, and you have these poor cattle that with 1 foot right in front of the other, they're just trying not to topple over into the river. Again, it's a little bit harder to figure out what the biggest value of X can be. We have an X over here, and we have an X over here. We have 2 sides of length X and 1,000 meters of fencing altogether. The bigger X gets, the smaller Y gets. The smallest Y could possibly be is 0. What's the biggest value of X that makes any kind of sense? If Y is 0, what does X turn out to be?
500.
500, right. The biggest value we could possibly have is 500. If X is 500, we just have this stupid looking pasture where we run 500 meters of fencing straight up from the edge of the water and then 500 meters back. And you better have pretty skinny cows if they're going to fit between that because there's no width. But it can't be any bigger than that. So here we are, a function, an interval. Step 5, go ahead and solve the problem. So let's find our critical points. A prime equals 1,000 minus 4x. Set A prime equal to 0. So 1,000 minus 4x is equal to 0. So 4x equals 1,000. Or x equals 250. At least that's a nicer number than we had last time. And we don't have to get rid of it because 250 is between 0 and 500. Make your chart. We're going to plug in both endpoints, 0 and 500, and this critical point, which happened to be right in the middle, but we saw from our first example, that's not always going to be the case. You plug in 0, you get 0. If you plug in 500, you get 0. If you plug in 250, I think you get 125,000. And comparing these three numbers, 0, 0, and 125,000, to me, that looks like the biggest. So again, I asked for the dimensions, the length and the width. So X is going to be 250 meters. And Y is going to be, well, we know we can get Y. We have X, 1,000 minus 2 times 250, 500 meters. So at least this one had a nice answer that has no decimals or anything in there. Don't forget to put units in your answer if there are units in your question. Do you have any questions? In that case, I will see you all on Friday. Take care.
Thank you.
Have a good day.
My pleasure. You too.
Professor,
Yes.
can I chat with you after class today?
Yes, I do have another class coming up in 10 minutes.
I'll take like
But but yeah, I have a couple minutes if you want.
Yeah.
So
Did you happen to get my email?
I did.
Okay.
So was this about the technical issue with the exam?
Yeah.
So what's the situation right now?
So it was like my fault. I don't think it was really a technical issue. I think it was, I'm gonna claim ignorance on this one because I didn't get an email for the exam and I wasn't able to attend class Friday. So didn't really think we had an exam over the weekend. So I didn't know. And it's like my fault.
You know, it was on the syllabus.
Yes, it was. And that's why I'm saying that's my fault.
So
Yeah.
what I want you to do is go ahead and take it. There's going to be a late penalty, but go ahead and take it.
Okay.
A
Thank
late
you.
penalty is way, way better than zero.
Oh, for sure. All right. Thank you.
You're welcome. Take it today, please.
I will.
Great.